Hello everyone. In the video today, we're going to talk about Taylor series. We're going to talk a whole bunch about them. So what's going to be covered in this video, we're going to talk about the definition and the derivation of a Taylor polynomial. We're going to talk about how to build a degree n Taylor polynomial, how to use Taylor polynomials to approximate a real number, then how to find the maximum error in that approximation. We're going to build infinite Taylor series, so with infinite number of terms instead of just stopping at 3 or 4. We're going to learn how to use known Maclaurin series to find power series representations of more complex functions, and how to calculate the radius of convergence and interval of convergence for a given power series. So what's not covered in this video is integrals and derivatives of Taylor series and power series, and then applications of Taylor series that we learned this past week, like evaluating limits, using them to approximate definite integrals, and using them to find the exact sum of a series. So that might come in a later video. Alright, so Taylor polynomials, the motivation behind them is to approximate complex functions with polynomials. At this point, you've probably heard me say this like 100 different times. But why use polynomials? Polynomials are easy to integrate and differentiate and work with in general, and evaluating a polynomial only involves addition, subtraction, multiplication, and division. Nothing fancy like a square root or a cosine or sine or anything like that, just the 4 basic things that you learn in elementary school. That's why we like polynomials so much. Who? This hunk over here. This is Brooke Taylor, and some students told me today that I have Riz, and I got nothing on this guy. Look at this hat. His hat is superior. I mean, I have a bird hat which comes close, but this hat is amazing. This guy's like in his pajamas teaching us about perspectives right now. It's pretty impressive. All right, let's get into it. How do we build a Taylor polynomial? Well, we're going to start with the equation of a tangent line at x equals a, and that's x equals a, not x equals a factorial. So you learned in Calc 1 that you can use the equation of a tangent line to approximate values close to a. And so here I have a function sine x, that's the red one, and then I have at 1 the equation of the tangent line, which if I use this formula is sine of 1 plus cosine of 1 times x minus 1. And you can see, like, very close to 1, it looks like it's working out okay. But the farther away we get, the worse the approximation becomes. This is pretty good for values close to x equals a. In this case, a is 1. But this is a curvy graph, and the farther away we get, the worse the estimation. So what do we do about this? How can we get a better approximation? Well, we can use the second derivative, which talks about concavity, to match the curviness better. A line is always going to be straight with no curviness at all, so the more derivatives we add, the better. And just a quick side note, this value, a equals 1, is called the center. And we can move that around, but x minus a, in this case, we're subtracting 1, so the center is at 1. So when we add a quadratic term to our equation of the tangent line, it becomes this. I highlighted it in black here. We just add c2 times x minus a squared. But we don't yet know what c2 is. However, we can make a restriction. Since we want the curviness to match in our approximation polynomial function and the complex function, we'll make a restriction that the second derivatives have to be equal. We are stating that they are equal. Well, we can take the second derivative of this polynomial and note that here we have a constant term. That will go to 0 right away. Here we have a linear term, and 2 derivatives of a linear term will also go to 0. So really the only one we care about taking the derivative, the only one we need to think about is this last term. So if we take the second derivative of this last term, we'll do power rule, bring down the 2c2x, and then we'll just have the coefficient 2c2. So we get that the second derivative, after we actually compute it, do the work for computing it for the polynomial, is 2c2, and we want that to be equal to the second derivative, and this sets us up perfectly because now we have an expression for c2 in terms of the second derivative. c2, if we solve this middle and right side of the equation, divide by 2 on both sides, and we'll get that c2 is the second derivative of x over 2. That works out very nicely for us. So replacing that here, we have our second degree Taylor polynomial, or another way to say this is our quadratic approximation is f of a plus f prime of a x minus a plus f double prime of a over 2 x minus a squared. And here I graphed again sine x, and this time the bonus part, the bonus quadratic term, and you can see that it's a lot closer. It still like misses farther away, like at 0 it's pretty far away, but the approximation is better, and that's what counts. It's a better fit. And to get an even better fit, we're just going to keep adding higher degree terms. And the higher order derivatives will just add on to matching the curviness of our functions better and better and better. Let's add a cubic term to our equation to the tangent line. The cubic term will be x minus a cubed with some coefficient. So that's what I wrote here. C3 times x minus 3 cubed. Again, we'll make a restriction so that the third derivative of our approximating polynomial will be the third derivative of x. So the rate of change of the rate of change of the rate of change will be the same. And if we take the derivative of this, again, everything that's less than degree 3 will go to 0 after we take 3 derivatives. So we're only focusing on this part that I highlighted in black here. If we take the derivative once, we'll get 3 c3 x minus 3 squared. Then we do power rule again, multiply down by the 2 and then the 1. So we get 3 times 2c3, and we can divide over and get that the coefficient here is the third derivative of f of x over 3 times 2. And it should be at a, but that's a quick fix. So now consider a degree 100 Taylor polynomial. I use the dot notation, the but notation here, to say we stop at 3 and then we go, yep, keeps going, following the pattern, and then C100 x minus a to the 100. So let's think about what we would need to do here. To find the C100 coefficient, we'd look at the 100th derivative of each part of this function. So everything other than this will go to 0, because if we take 100 derivatives, it'll eventually just all go to 0. So if we take 100 derivatives by power rule, first we're multiplying by 100, then we're multiplying by 99 because we subtracted 1 from the exponent, then 98, then 97, 96, all the way and down until we get to 1. So that will look like this: 100 times 99 times 98 times times 3 times 2 times 1 times our coefficient equals the 100th derivative of f of x. Well, we have a shorthand notation for this big product. We would just write it as 100 factorial. And then if we divide that over to the right, we have C100 is equal to the 100th derivative of x over 100 factorial. And again, I should be substituting an a here for that coefficient everywhere here. For f double prime, for f triple prime, that should be at a. But the idea is the same. The harder concept is there that for each coefficient, we just take the nth derivative at a and divide it by n factorial. So let's generalize this. In general, for the nth coefficient, we take the nth derivative at a divided by n factorial. So using a sigma notation to condense this, because we don't want to write an infinite number of terms here, or just 10 terms I don't really want to write, we'll use sigma. And we'll use this notation. You can use a t or a p, doesn't really matter, but I tend to use t for Taylor polynomial, of degree n is equal to the sum from k equals 0 to n of the kth derivative of x over k factorial times x minus a to the k. And again, I keep messing this up by accident. This should be at a. So the kth derivative at a, not at x. But let's use that, and again, it's at a, but that's what we do here. Let's take a look. If we want to find a quadratic approximation for e to the x centered at 0, we are going to take degree 2 Taylor polynomial. That's what quadratic means, degree 2. If we're looking at a degree 2 Taylor polynomial, it means we need to take 2 derivatives. So we write the function, again, f of x equals e to the x, and then we take 2 derivatives, which is very easy in this case, just the same thing, e to the x. This next part, we're going to plug in the center. So if we plug in 0 for each of these, we're going to get 1 every time. Convenient. For the next part, we're going to divide each of the numbers we just found by n factorial. that will get us the final coefficients. So C0 is 1 over 0 factorial, which is 1. C1, 1 over 1 factorial, which is also 1. And then C2, 1 over 2 factorial, which is 1/2. And here, x minus a is 0 because it's the center. And then we'll just have x to the 0 power, x to the first power, x to the second power. And we'll write that as 1 plus x squared over 2. And this is our final answer here. This is our quadratic approximation for e to the x centered at 0. And let's get a visual representation of this. In red is our e to the x, and blue is the quadratic function that approximates this. And again, at 1, they have exactly the same, at 0, they have exactly the same value. And then the farther we go away from that in either direction, the worse the approximation gets. Let's do another example. This one's a bit more complicated. Create a Taylor polynomial of degree 3 to approximate the function f of x equals the fourth root of x minus 1 centered at a equals 2. There's a lot more going on here. The derivatives are going to be more complex. We have to take more of them. And the center is at 2 instead of 0. So let's see what we get here. The function is just going to rewrite it, but write it in fractional exponent form instead of a radical. So x minus 1 to the 1/4. Derivative, 1/4, x minus 1 to the negative 3/4 by subtracting 1. Second derivative, again, we're just applying power rule, and the third derivative, applying power rule again. For this next part, we are going to plug in our center. So this is like, I forgot the a here again. I keep forgetting the a everywhere. But we'll plug in a equals 2 here. So for the function and all its derivatives, we'll plug in 2. This is very nice because 2 minus 1 is 1. In each case, doesn't matter what the crazy exponents are. 1 to any power is 1, which means we're just going to get these coefficients on the side. So 1, 1/4, negative 3/16, and 21 over 64. Next up, we're going to divide by 0, 1, 2, 3 factorial, like we did in the first example. And again, we're just taking the numbers we just found and dividing them by that factorial. 0, 1, 2, 3, respectively. When we simplify that, we'll get a 1, 1/4, negative 3 30-seconds, and 7 over 128. And the last part is just to put this together with the polynomial part, with the x minus a to the n. So here, since it's the constant term, we're just going to have 1. The next term is going to be 1/4 times x minus 2 to the first power, but we're not going to write to the first. Then this coefficient times x minus 2 to the second, and then this coefficient times x minus 2 to the third. When we put that all together, it'll look like this. The third degree Taylor polynomial is 1 plus 1/4 x minus 2 minus 3 over 32 x minus 2 squared plus 7 over 128 x minus 2 to the third. And again, let's take a look at how our approximation looks relative to the actual function. In red, we have the fourth root of x minus 1, and the blue is showing our approximation. And between like 0 and 5, it's like looks like it's a really good approximation. All right, let's use this Taylor polynomial to approximate an actual value. So let's use this to approximate the fourth root of 3. So let's consider the fact that the function that we started with, that we wanted to create the Taylor polynomial for, was the fourth root of x minus 1. And that is approximately t3 of x near x equals 2, which was the center. So we'll just substitute x equals 4 into t3. And we're getting the 4 because we're thinking, all right, well, how do we get the fourth root of 3 for our original function? If we're subtracting 1 on the inside, then what number minus 1 gives us 3? So if we're plugging in 4 to our function, we're also going to plug in 4 to our polynomial that's approximating that function. So if we plug in 4, we'll just replace all the x's with 4's in our polynomial. We simplify. This is easy enough to actually do the math without a calculator. And we will get 25 over 16. So we used our polynomial to actually approximate a value of our complex function. But now the question is, we have the fourth root of 3 is approximately 25 over 16. Is this good? Is this a good estimate? How would I know? Like, I have no idea what the fourth root of 3 is, and I can kind of think about how big 25 over 16 is, but how do these compare? Is it a good estimate? Is it bad? And how can we tell without knowing the exact value of the fourth root of 3? Well, we'll use something called the Taylor remainder theorem. And this big scary thing looks like this. We talked about it in class today or yesterday, depending on when you're watching this video. And it looks like this. And it looks kind of familiar. It looks like the Taylor series at n+1, except that instead of evaluating, the derivative at a, we're evaluating at some value c, which works with the mean value theorem to get us the remainder. So this value is really hard to come up with. Like, finding the number c is a whole other page of work in itself. So instead, to save a lot of time, we're just going to replace it with an upper bound. So that means we're going to look at that derivative, the n plus first derivative, and then maximize it over some interval. And this is what we're going to state, that m is greater than or equal to f of n plus 1 of c, so the n plus first derivative of c over the entire interval. All right, let's do it. Let's estimate. So some things we know about our function is that it's degree 3. By design, that's what we created, a degree 3 polynomial for the fourth root of x minus 1. We know a is 2 because that's the center. That was also given to us. And x equals 4 is what we're plugging in to approximate the fourth root of 3. We plugged in x equals 4. And just a quick note, when we're not explicitly given an interval, we'll use a and x, the center and what we're plugging in, or x to a, whichever one is smaller to whichever one is bigger. So in this case, since a is smaller, our interval will be from 2 to 4, and 2 and 4 are the endpoints we'll test out in the derivative. So let's do that. Let's maximize the n plus first derivative. So we know n is 3. We did the third derivative already. I'm just copying and pasting this from the work we did before. And now let's take the derivative one more time to get the fourth derivative. Fourth derivative is negative 231 over 256, x minus 1 to the negative 15 over 4. I'm going to rewrite that so the exponent is positive, which means I'll drop that in the denominator. And now we're thinking about 2 and 4 and which number would produce a larger result in this derivative. And so since the variable is in the denominator, a smaller number in the denominator would lead to a bigger overall expression, and we want a bigger upper bound. So x equals 2 would work because that would be bigger than the fourth derivative at x equals 4. And that's also really nice for us, again, because if we plug in x equals 2, we get 1 to the 15 over 4, which is just 1. And so because we want the absolute value, we'll get m equals 231 over 256. Now that we have that, we can just put everything we know in. We know n, a, x, and m. So plugging that in, replacing all the n's with 3's, replacing the a and x with 2 and 4 respectively, and replacing the fn plus 1 of c with our value for m, 231 over 256. We can plug this all in, and we'll get 0.602 for our maximum upper bound, which is not a very good approximation. It's not very good at all. If we wanted better, we could just take more terms of our polynomial or move the center closer to 3 or closer to 4. Awesome. Now I'm going to have you try this one on your own. I'm going to show the solutions but not talk about them too much. So find a Taylor polynomial of degree 3 for f of x equals square root of x centered at 4. Use your polynomial from part A to approximate square root of 5. Find an upper bound for the error in your approximation from part B. And then find an upper bound for the error in your approximating function on the interval 2, 6. So what's the biggest difference between your approximation polynomial and your function over that interval? So I recommend pausing it now before I go and show the solutions and try and solve each of these on your own. All right, let's check out the solution. So degree 3 Taylor polynomial is listed here. All the work is shown here, so you can pause it if you need to. I'm just going to head to the next solution. For B, using your polynomial to approximate square root of 5, we'll get this fraction. You can also write it as a decimal, but I wrote it as 1,145 over 512 because it's still a decently nice fraction. Then for the error, upper bound in the error, we do all the work like we did in the last example. We have 4 and 5 that we would test with the n plus first derivative. So here's the work for the n plus first derivative. If we plug in 4, it's greater than if we plug in 5. And so we will do that, and we'll get a result of 15 over 2048. And then here is the work for plugging in all those values, n, a, x, and m. And I left my answer here in scientific notation just because it was a little bit easier. And then this last part I do want to talk a little bit more about in detail. Find an upper bound for the error for the whole function on this interval. Since we're not given an explicit value, we're given this interval instead. Instead of saying x equals the thing we're plugging in, we're going to say x is in the interval that they gave us. And then instead of using a and x for our testing of the derivative, we are instead going to use the two endpoints of the interval. So 2 and 6 in this case. And again, we get this thing. Oh, that should be a positive exponent. Just a heads up there, that should be a positive exponent. Because we put in the denominator. If we plug in 2, it should be greater than 6. And when we do, we'll get this decimal. And we'll plug everything again like we did before. But again, x is either going to be 2 or 6. We want to take the number that will give a larger overall result. It doesn't matter in this case because 6 minus 4 and 2 minus 4 are going to give the same number in absolute value. And so we do all the math here, and we'll get 0.0553. And I want to make a note here that in rounding off the m and rounding off the final answer here, I'm like rounding up always because it always needs to be bigger than your long decimal in your calculator. So if this was 0.055293 whatever, then I round up to 3. Even if it was 0.5522, I would still round up to 0.553 so that I make something bigger than what we see in the calculator. All right, let's move on to building infinite series. Build a Taylor series. So a Taylor series has infinitely many terms. This means we'll use sigma notation to compact it. And our strategy for this is to build the 4th degree Taylor polynomial and then find the patterns. At least for things like cosine, sine, e to the x, this strategy will work out nicely. So quick note, Taylor series centered at a equals 0 have an extra special name, Maclaurin series. And as you can tell, Maclaurin also has the Riz, for sure. Look at that hair. Who needs a hat when you have hair like that? All right, let's get to it. We're going to write the function, and since we're starting with the degree 4, we'll take 4 derivatives. These are pretty quick, so I'll just scroll through them quickly. It's just the derivative of sine and cosine that we know. Then we're centered at 0, so we'll plug in 0 everywhere and get these values. We'll divide by 0, 1, 2, 3 factorial, 4 factorial, respectively. And note that we get 0 for 2 of the coefficients. If we get 0 for the coefficient, 0 times x minus whatever is going to be 0. So I'm just going to skip those terms. Here, the constant term is 1, skipping over the 0 term. Then we'll have a minus x squared over 2 factorial, skipping the next 0 term, and then plus x to the 4th over 4 factorial. If we put this together, we will get the 4th degree Taylor polynomial for cosine is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And quick note that the degree is not always the same as the number of terms. The degree is the highest exponent you have in your polynomial. So a common mistake would be to say that this is degree 3 because there's 3 terms, but it's 4 because the highest exponent here is 4. Okay, so we have this degree 4 polynomial, but what we want is degree infinite polynomial, and so we need to find a pattern with these first 3 terms. So we're going to build this piece by piece. It's blank right now. We just have some sigma from 0 to infinity. And the first thing we're going to notice is that we start positive, and then negative, and then positive. That means it's alternating, and it will be with -1 to the n, because when we plug in 0, that first term is positive. The next thing to notice is that the powers of x are going up by 2. We have 0, 2, 4. If I wrote another term, it would be x to the 6th. So to write even powers, that would be x to the 2n. And then the last part is that we're also dividing by that same number, but with a factorial outside. So we're going to write the same thing, 2n, but with a factorial at the end. And there we go. There we have it. That's our Taylor series for cosine x. It's an infinite number of polynomial terms that all add up and converge to cosine. Next thing I want to do in this is use a Maclaurin series, which is what this is. This is a Maclaurin series for cosine x. Use a known Maclaurin series to find the Taylor series for something more complex, for something that we really don't want to go through this process with, because taking the derivatives is really hard. So our first example here, write the power series representation for f of x equals 2x to the 9th of arctan, 2x to the 9th times arctan x to the 5th over 3. And we're going to start with the power series representation of arctan of x. This will be given to you in a reference sheet, so this is what we're going to start with. We're just copying this and pasting it from the reference sheet. Next, we are going to compose this x to the 5th over 3 on the inside. So I'm replacing it on the left and in the right. So wherever I see x, I'm replacing it with x to the 5th over 3. Then we're going to break up this fraction as x to the 5th to the 2n plus 1 and 3 to the 2n plus 1. I'm leaving the x to the 5th on the top, but I'm going to put the 3 to the 2n plus 1 on the bottom. And then we'll simplify this x to the 5th to the 2n plus 1 by distributing the 5 through this 2n plus 1. And that'll give us what we have so far, that arctan of x to the 5th over 3 is represented by this series, and the only change that we made is we have a 3 to the 2n plus 1 on the bottom, and an x to the 10n plus 5 on the top. So that's the first part. Next part is to consider this x to the 9th. So I just copied and pasted what we just got with the x to the 5th over 3 inside. And now we're going to consider multiplying by x to the 9th. But the good news is it's pretty straightforward. We have x to the 10n plus 5. We have x to the 9th. They're exponential expressions that have the same base, so we just add their exponents. 10n plus 5 plus 9 would be a 10n plus 14. Awesome. And the last thing here is the 2 out front. But the constant is even easier than the last part. We're just going to leave it outside of the series. Kind of like in an integral, you can leave that constant on the outside. And then we are done. The power series representation for 2x to the 9th arctan of x to the 5th over 3 is this. And imagine trying to do this the original way we did, which is take the function and like 3 or 4 derivatives and then plugging in 0. It's going to be an absolute nightmare. So very grateful that these properties exist. Let's try another one. Write the power series representation for f of x equals e to the negative x cubed over pi. So starting with the power series representation of e to the x, which will be given to you, we are again going to start with the substitution, replacing x with negative x cubed over pi. And this time we have 3 things to break apart. We have the negative, which we'll take out as a -1, the x cubed, and the pi. So we have a -1 to the n, the x cubed to the n, and a pi to the n, which I'm pushing to the bottom. Then, last thing to do here is just simplify the x to the 3n as, x to the 3rd to the n as x to the 3n. Awesome. And now there's only one extra part here, and that's to multiply by x. So I'm going to multiply it on the left and the right. It's x to the first power. We have x to the 3n. So we'll add those exponents together when we multiply. And our final answer here will be negative 1 to the n x to the 3n plus 1 over pi to the n times n factorial. So not so bad. We just got to get used to it. And these are kind of fun. I especially like the substitution part. It's kind of fun. All right. Next, I want to talk about radius and interval of convergence. So we just stated before that e to the x is represented by this infinite series x to the n over n factorial. And whenever we have an x to some power in a series, we call it a power series. And it's called a power series because of the power. But I want to be more precise here and say that instead of representing a single series, this power series represents a family of series. X is a variable, so x could be any number that we want it to be. So our next goal is to figure out for which values of x does this series converge. If x equals 1, does it converge? If x equals 2, does it converge? Does it matter? Does it converge for all numbers, for only one number? What's going to happen with different values of x? So our approach will be the same no matter what power series we're given. It's going to be to run the ratio test and then use that result to know what happens. And just as a quick reminder, I didn't write it here, but the ratio test says that if you take the limit of the ratio between the an plus 1 term and the anth term, and you get less than 1, then it converges, greater than 1, diverges, and equal to 1, the test is inconclusive. So an assumption I'm making right now is that you are comfortable with the ratio test, in addition to some of the other convergence tests that are going to come up inside of this when we test endpoints. So find the radius of convergence and interval of convergence for the given series. This is how this question will be stated. Here is our given series, which is the representation of e to the x. So let's run the ratio test. We're going to replace all the n's with n plus 1s, x to the n plus 1 over n plus 1, and then multiply by the reciprocal because it's almost always going to be a fraction. So when it is a fraction, instead of dividing and getting a big fraction, we're just going to take the shortcut and multiply by the reciprocal. Okay. And I forgot the factorial here, but we can fix that. So this should be n plus 1 factorial. And we have one more x on the top than the bottom. And if I write this correctly and have n plus 1 in parentheses factorial, then we have n plus 1. I made another mistake here. Can I fix that? I don't think I can fix it while I'm presenting, but I made a mistake here. This should be n plus 1 because this is n plus 1 factorial. So we have n plus 1 on the bottom. Not going to really change the final answer, but it's good to be correct. We have n plus 1 on the bottom. Please fix that for me in your notes. And by ratio test, if we take this limit, n is the thing that's growing, and x is just a number. So if x is some number and n is going to infinity, then this whole expression is going to 0. And by ratio test, this series is going to converge regardless of the value for x. So if it's going to converge for any value of x, that means the radius of convergence is infinity. And the interval of convergence is negative infinity to positive infinity, meaning all numbers. Any number you put in will give you a convergent series. Awesome. Let's take a look at another one. This one is a little wackier. 3x minus 2 to the n over n times 3 to the n. But, like I said before, we start the same way every time, by the ratio test. Let's set it up, replacing all n's with n plus 1s. 3x minus 2 to the n plus 1 over n plus 1, 3 to the n plus 1, and then multiplying by the reciprocal of what we started with. So n3n is now on top, and 3x minus 2 to the n is on the bottom. So if we look at the 3x minus 2's, we have one more on top than on bottom. If we look at the 3's, we have one more on bottom than on top. And then we'll just leave the n and the n plus 1 alone, but kind of lump them together. So then we'll get this, 3x minus 2 over 3 times n over n plus 1. And when you take the limit as n approaches infinity, we recognize that this is a rational function where the degree of the top is equal to the degree of the bottom, which means we take their coefficients, and their coefficients happen to be 3x minus 2 and 3. So this limit converges to 3x minus 2 over 3. And by ratio test, this limit will converge when r is less than 1. So we're going to take this absolute value expression of x and set it less than 1 to find all the values of x for which the series converges. So let's take a look at how to solve this weird absolute value inequality. We have 3x minus 2 over 3, absolute value less than 1. We can get rid of the absolute value and put it between positive 1 and negative 1. And you can do that whatever this number is. If it was 7, then we'd have a negative 7 here on the left. Next, we're going to multiply by 3 on all sides. So negative 3 less than 3x minus 2 less than 3. Next, we're going to add 2 on all sides. That'll give us a negative 1 less than 3x less than 5. And then we're going to divide by 3 everywhere. And this is our initial interval of convergence between negative 1/3 and 5/3. But we need to test the endpoints to know if the series converges at those points as well. And we need to test that because we don't know. The radius of convergence doesn't tell us about the endpoints. So to test them, we are going to go back to our power series and plug in x equals negative 1/3 to see if it converges at that point. We already know it converges at 0, at 1, because those numbers are within our interval of convergence, but we're not sure about these two specific endpoint numbers. So let's do the math here. If we plug into the initial series, 3 times negative 1/3 is negative 1. Negative 1 minus 3 is, minus 2 is negative 3 to the n. We can take out that negative, and then 3 to the n divided by 3 to the n is 1. And then we'll have negative 1 to the n over n. This is the alternating harmonic series. We've done this before. I'm kind of skipping some work here and showing that it's decreasing so we can use the alternating series test, but it will converge by the alternating series test. We take the limit as n approaches infinity, we get 0, so it does converge by alternating series test. Next, we're going to test x equals 5/3 by the same process of plugging it into the original power series for x. This time, we'll get the 3's to cancel, 5 minus 2 is 3. The 3 to the n's will cancel, and we'll get 1 over n. That's just a harmonic series, which we know diverges by p series. So if it diverges, nothing to do, nothing to change. But if it converges, we are going to change that inequality to less than or equal to, because it does converge at negative 1/3, so we need to include it in our set of x values that converge, that make the series converge. Okay. We still have to figure out what the radius is, and it's a little bit tricky in this one because we have some not super nice fractions. But the radius of convergence is defined as the distance between the center and one of your endpoints. So if we know what the center is, we can just use one of our endpoints and subtract to figure out what the radius is. So if we want to know what's the center, it would just be the middle of these two numbers. And if you want to know what's exactly between two numbers, you take the average. So we're going to add them up and divide by 2. Negative 1/3 plus 5/3 divided by 2 will give us a 2/3. And then if we take that and we run 5/3 minus 2/3, the endpoint minus the center, we will get 1. So the radius of convergence is 1 with a center of 2/3. Let's think about that for a second. If the center is 2/3 and we add 1 or 3/3, 2/3 plus 3/3 is 5/3, and 2/3 minus 3/3 is negative 1/3. So it seems like it's correct. Our radius of convergence is 1. All right, last example. Whoops, that's supposed to be hidden. That's okay. Here's our given power series, n factorial times 2x minus 1 to the n. We're going to run the ratio test, replace all the n's with n plus 1s, and then divide by the original. This time it's not a fraction, so we don't have to worry about multiplying by the reciprocal. There is going to be left with an n plus 1 on the top. There's one more 2x minus 1 as well. But there's only just n in the top, and if n is the only thing that's growing and it's going to infinity, then the whole expression is going to go to infinity, regardless of x. So by ratio test, this series diverges regardless of the value of x. That means that the radius of convergence will be r equals 0. And that will always be true if your ratio test diverges for your power series. The interval of convergence will be the center or the value of x that sets the limit to 0. we haven't experienced something that looks like this, 2x minus 1. So like we may not be sure what the center is based on this. But we can go back to our limit, our last line of the limit, and think about what value of x would make this 0. And the value of x that would set this to 0 is 1/2, which is also the center. So the interval of convergence in this case will be 1/2. Just 1/2 is the only value that this will converge for. Whew. All right, we made it. I don't have cats, but I have Zoe's reaction to my cool new bird hat. What is this? Yeah, a sentiment that we often share when learning calculus. All right, y'all. I hope you enjoyed that video. I had a fun time making it, and I hope it was helpful. Taylor series is some tough stuff, and I hope this made it at least a little bit easier. I'll see y'all in the next video.